Integration by reversing the chain rule. Let y equal the composite function f of g of x. Then the first derivative, y dash, is equal to the derivative of the outer function, f dash of g of x, multiplied by the derivative of the inner function, g dash of x. Reversing this, the integral of g dash of x times f dash of g of x dx is equal to f of g of x plus c. So we go back to where we started. Now it is important to identify when reversal of the chain rule is required when integrating. So if the integrand is in this form, or a multiple of this form, then reversal of the chain rule is required. Here's a quick example. If we let y equal sine of x to the power of 5, then dy dx is equal to 5 times sine of x to the power of 4 times cos of x, which is equal to 5 cos of x times sine of x to the power of 4. Reversing this, the integral of 5 cos of x times sine of x to the power of 4 dx is equal to sine of x to the power of 5 plus c. Example 1. Find the integral of x times 3x squared plus 1 to the power of 5 dx. Now the integrand is in the form k times g dash of x times f dash of g of x, which means that the primitive of this function must have had an index of 6. Now we're going to let g of x equal 3x squared plus 1. That's the inner function. And f of g of x is equal to 3x squared plus 1 to the power of 6. So we need to determine what this constant k is. Now if we take the derivative of f of g of x, that equals 6 times 3x squared plus 1 to the power of 5 multiplied by the derivative of the inside function, which is 6x. So that equals 36x times 3x squared plus 1 to the power of 5. However, if we go back to the integrand, we only have x times 3x squared plus 1 to the power of 5. Hence, 36 times the integral of x multiplied by 3x squared plus 1 to the power of 5 dx must equal 3x squared plus 1 to the power of 6. Of course, there'll be a plus c somewhere, but we'll include that at the end. Therefore, dividing both sides of the equation by 36, we have the integral of x times 3x squared plus 1 to the power of 5 dx is equal to 1 over 36 times 3x squared plus 1 to the power of 6 plus the constant c. Example 2. Find the integral of 3x over the square root of 2x squared plus 1 dx. Now the integrand is in the form k times g dash of x times f dash of g of x. Now it helps to note that if we started off with the square root of a function, now in this case the square root of 2x squared plus 1, and then took the derivative, you're going to end up with a fraction whose denominator is going to involve a surd. After all, the power of half is reduced by 1 and becomes negative half. So let f of g of x equal 2x squared plus 1 to the power of half. So it's a composite function. Then dy dx by the chain rule is equal to half times 2x squared plus 1 to the power of negative half. Notice that that's where this denominator comes from. Multiplied by the derivative of the inside function, so multiplied by 4x. Simplifying all that, we get dy dx is equal to 2x over the square root of 2x squared plus 1. And notice that that resembles the integrand. Now if we reverse this, the integral of 2x over the square root of 2x squared plus 1 must be what we started with, the primitive function 2x squared plus 1 to the power of half, or the square root of 2x squared plus 1. However, we want to integrate 3x over the square root of 2x squared plus 1. So we need to involve taking out a factor outside the integral. So hence, the integral of 3x over the square root of 2x squared plus 1 dx is equal to 3 over 2 times the integral of 2x over the square root of 2x squared plus 1 dx. And we know what to do with this now. That's just equal to 3 over 2 times 2x squared plus 1 to the power of half plus the constant c. And expressing this in surd form, that equals to 3 over 2 times the square root of 2x squared plus 1 plus the constant c.